Okay, today we are glad to have Mr. Ninan Kiran Gaikwad. He's our PhD student at WSU. So he's doing his PhD and in electrical engineering and also master degree in computer science at Washington State University. He expecting to graduate fall 2025, but who knows that? Yeah. In addition, yeah, we will see that. In addition, he holds a master's degree in mechanical engineering from University of Florida. He got that degree in 2021. Master of Technology in Power Electronics and Power System in 2016. A Bachelor of Technology in Electrical Engineering in 2012. And as his PhD work, he is focusing on the developing efficient building thermal models for intelligent control of network building. Also, he is working on, he's interested in working on physics-informed machine learning, model predictive control, and reinforcement learning for energy system optimization. So that's, with that one, floor is yours. So back to you.
Thank you. Good afternoon, everybody. Today I'll be talking about intelligent control of network buildings, a conceptual framework. So there wouldn't be a lot of results, but like it would be a journey going from the concept to what the bird's eye view is for this field. So let's start. Okay, so the outline of the presentation would be, we would go through a motivation, we'll do some mathematical modeling, understand some model estimation algorithms, understand the basic optimal control paradigms, and then we conclude the talk. So for motivation, okay, so firstly, we have the duck curve problem. Like even when we are, even do we want to have a lot of intermittent solar into our mix so that we can become, we can decarbonize and become more green in our energy usage. It is all good on that side, but for system operations, it causes a problem. As you can see, the net load curve, this is from KAISO, and this is like a projection for 2020, and the actual was 2012 and 2013. And as you can see, the net load, which is nothing but the total generation minus the solar generation, the steepness during the evening time, the ramp up that is required, needs a lot of dispatchable generation. And a few of the possible solutions, or rather the possible solutions are dispatchable generation, like natural gas power plants, hydroelectric power plants, energy storage at utility scale in the form of battery, thermal or chemical storage. But all these solutions require capital investment. And we do not want to use natural gas power plants to be fired or natural gas to be used if we want to utilize clean, green energy from solar. So there is another way, another possible solution, which is energy demand management, or as we call it, demand response programs. So utilizing this in conjunction with the other two, we can try and solve this problem of the duck curve. And in this talk, we will focus on energy demand management in buildings, or rather network buildings at scale. So why buildings? Like what is so important about buildings? So firstly, this data is from energy, okay, it is from EIA. I always forget their acronyms full form, but as we can see, like out of the total consumption within a building for different things, space heating and cooling is about 41%. So that is the HVAC system, which is 41%, which is being utilized in a building. And that provides us with a dispatchable load, because buildings have inertia. Like if you turn off the AC or turn off the heating within a building, the temperature of the building wouldn't change instantaneously, but rather it would take some time because the building has thermal inertia. And this characteristic of the building, thermal characteristic, can be exploited in a demand response paradigm. The other thing to note is that out of the total energy usage in the United States in 2022, 22% was used by residential buildings. And out of that, 51% was used for HVAC. Whereas in commercial buildings, 18% of the total energy usage in the US was done by commercial buildings, while 41% of that was utilized for HVAC. So HVAC is a big consumer of energy, and if we can maneuver that, we have enough flex, as we can call it, to help with the problem of the duct curve. All right. So knowing that, let us start doing some mathematical modeling. All right. So this is a basic building schematic, and it is supposed to be very general. So building can have DER sources like solar PV on the rooftop, some battery storage, maybe there is parking where you can actually plug in electric vehicles. And for this talk, we say that the electric vehicles can actually charge and discharge with some control. And then we have the HVAC load for heating and cooling in the building, the other electric load like lightings, equipment, and then there is the elephant in the room, the building thermal model, which we'll talk about in detail ahead. And all these things, so this comprises of a building, which is not a passive thing, but rather an active, can become an active participant in the energy grid. And this building's behavior is basically dependent upon the ambient weather, how hot, how cold it is outside, and what are the people doing inside of it, right? So if we leave the building at 5 o'clock from a commercial building, go to our homes, the building energy consumption drastically reduces. So those are the disturbances that affect the performance of the building. And yeah, and we can compute finally what is the total energy consumption or production in a building from once we have all the models with us. So let us look at some simple models, which are the solar PV model, which basically depends upon GK, that is the global horizontal irradiance, and TMK, that is the module temperature, where the module temperature is dependent upon TAM, which is the ambient temperature. And this model, once you know the PV rated, so basically what I'm trying to say is that model, once you have a specification of PV sheet, you have that model, like end of story. You don't have to do much with it. Similarly, a battery storage model can be shown to be something like this. It is a bucket of energy, the EBAT or the energy in the battery at the next time point is basically what there was before, and how much was added or subtracted from it, from discharging or charging from it. So that's the battery storage model. And if you know your battery, you would definitely know from its specification sheets what kind of efficiency does your battery have. So you know those eta C and eta DC over there. So you don't need to do estimation for that. And then you have electrical vehicles, and it is basically a battery. And the only thing extra in this one is the PK, which is basically, is it parked and connected, or is it not parked and away? So otherwise, it just acts as a battery. And the other electric load is like lighting, equipment, which can be basically modeled as some schedule of that load. So basically lighting, if we consider lighting in this room, so lighting goes from 0 to 1 as a schedule from 8 a.m. to 5 p.m., right? And then if everybody leaves, we would like to switch it off. So that is the S is the schedule of operation, and P rated is whatever is the rating of your lighting or other equipment. Next is the HVAC model. So the HVAC model, basically, we are very much interested in the PHVAC. That is, what is the amount of power, electrical power that the HVAC system is consuming in providing both heating or cooling. And in this talk, we would consider that buildings are cooled and heated with electricity and not gas, just for simplicity or the work that has been done. So that PHVAC is some function of QHVAC, and QHVAC is your thermal energy that is required to basically provide heat or reject heat from a thermal zone, and it is given by a physics equation which consists of Ca times supply air mass flow rate m dot, the zone temperature or the room temperature, and the TSI is the set point temperature of the incoming air. So that set point, if it is hot enough, hotter than the zone temperature, it will heat it. If it is cooler than the zone temperature, it would cool it. Right? And then a building thermal model can be actually very complicated. And we have an entire software called Energy Plus, which does a really good job doing this. And it can be, so heat equations can be solved as, heat equations are basically partial differential equations, but for us, we basically simplify the physics of the building thermal process into a 1D case, and hence we end up with ODEs, ordinal differential equations. And over here is one such case of an ODE where a zone, and a zone would mean any room or any volume within a building which would have a thermostat. That is a temperature within that volume can be controlled independently. And to represent that zone or the way the temperature evolves in that zone, you can basically write equations something like this, and they come out to be a thermal model. It basically can be translated as an RC network model, where every R is the impedance provided by the material for heat flow. And every capacitance is the capacity of that material to hold on to heat, so that temperatures, because we see that temperatures do not change instantaneously. And over here, you have the capacitance at the node. So to do an electrical analogy, your temperatures, the nodes are the voltages. The currents that flow are the heat flows. And with that simple physics, you can basically model the trajectory of, model basically the thermal process of a zone. Okay, is that clear? Yeah. Okay. So basically, having all that knowledge, we have developed a smart community simulator. It is in MATLAB, and basically, the plant is that you can, okay. So basically, what it does is you can simulate any arbitrary number of houses. Okay, it can be simulated here, and each house within that simulation can be heterogeneous or can be independent, can be either a house with PV battery or EV, just PV or no DERs, like you can choose. And then the disturbances provided over here come from the load data for the house, comes from Pekin Street. The weather data as a disturbance comes from NSRDB. And then we have provided predefined baseline and rule-based controllers so that there is some control so that people can start off using the simulator in its baseline cases. And then you can define your own user-defined controller to control this piece of simulator, or rather a group of houses. And the other good thing about this is it can simulate both on-grid and off-grid modes can be simulated in here. And each house comes with a HVAC, and it is up to you if you want to control it or not control it, depending upon, so it's very flexible. So this is something we have built based on our knowledge of the models. And there is something that we want to, or covet to have is, or rather, let us look at some results too. All right, so the baseline controller, this is an off-grid case. It is just a single house with PV and battery. It is off-grid, meaning it is just dependent on its PV and battery for energy supply. And as you can see, because the baseline controller is so dumb, nothing is served. Like you can see, it just, the temperature is not maintained. Your load is not, the desired load is not served. And so it basically says that the physics, the simulator is providing you with proper physics. At the time scale that we require it to be. And then we have the rule-based controller, which is a little bit smarter, or rather I would say a lot smarter than the baseline. And you can see that this is more like, okay, the temperature is getting maintained somehow. you are getting some desired load, like supplied by the battery and PV. So this basically is to show that the simulator is ready if anybody wants to use it for developing certain kind of an application. We have a simulator ready to do that for you. The other thing that we're trying to develop is a co-simulation workbench for where you can basically you will be simulating buildings, houses, smart communities along with OpenDSS. And we will be using Helix as the co-simulator enabler. And we would have a different Python scripts for recording the output of the co-simulation, a particular Python script from where you can actually do the control. Basically, that script would be an entry point to your control algorithm. We would definitely give you some basic algorithms like the ones that we have before. And then all of this will be handled by Helix. And that is what we want to develop so that we have this workbench going forward. So this work is in progress. And the idea is any arbitrary number of buildings can be simulated over here. Buildings can have heterogeneous DERs, or they can have none. They are just consumers. Each building will have its own controllable HVAC. And this should be used or can be used for simulation, controller testing, or if you're doing some data-driven control, this can be your the gym environment, so to say, to do that. All right. Any questions up till here? All right, then we move on to model estimation. All right. So all the models that we looked, like the solar PV model, the battery model, the other load model, all of those models we can just find out from specification sheets and knowing a little bit more about our building. But the thermal model, the RC network that you saw, that is difficult. Like you cannot just get it. Like nobody is gonna just give you the RC values. You will have to get some data and create your model, test it. And once you have that model, then you can do all those things in the simulator that we just saw. So how to do that is basically model estimation. And what we do here is, because of lack of real building data, what we started off with is the PNNL's buildings database. This is like a database of 16 different prototypical commercial buildings, and it comes with like 19 different weather files, and then you also have some residential buildings, and other two kinds of buildings are present. So what we do is we use those files to and pass them through Energy Plus, and Energy Plus gives us data. This data we process, and the data is basically what was the occupant and equipment data inside of it, what was the weather data, like what were the HVAC loads and zone temperatures, all the data that will help us build the model further down the line. So data processing is done, like once you generate the data, you do some data processing. We'll talk about it in the next slide, what we exactly do. And then there are two ways of handling this problem. Like you can either have a gray box, which is like a little bit a physics-based model, as you saw, like learning the RC parameters of the thermal network is a gray box problem. And while if you want to estimate the same behavior, but use a machine learning technique, then it would become black box. So we would try to explain both these things and show the progress of where we are at. All right, so data processing. So look at this. This is like a top view of a building, and this is the simplest commercial building available from PNNL. It is called the small office building, which has 5 zones. There is a central core zone, and then there are 4 perimeter zones. And when you would actually give the IDF file to Energy Plus and supply it with the appropriate weather file, Energy Plus would give us a zone, like for each zone, it will give us variables, which we can utilize to create our models, okay? But the whole idea is, because we want to simulate large number of buildings, we do not want the model to be complicated, okay? So yes, this building can be best represented by a 5-zone model. Okay, but what if we can reduce the number of zones artificially and get the same behavior that we require in our control application? So that's what we wanted to test. And for that, we basically start aggregating the zones. So if you just remove all the boundaries, or rather, you don't do that, you just aggregate all the 5 zones together as an average, you get one set of variables for this aggregated zone. Similarly, you can do it, maybe you are like, okay, this is just very bad, like you didn't get a good model fit after this. You're like, okay, maybe it can be done with 2 zones. And then due to the symmetry of this building, what you can do is, okay, I can consider this central zone to be one particular zone, and all other perimeter zones can be aggregated. And then you have a two thermal zones aggregation. And similarly, a 3 thermal zone aggregation, and you can see why not 4 zone, because there is no symmetry to do that exactly here. And out of this, like, you can either have, so the whole idea is, if we are able to get single zone model for any particular building to work well for our energy control application, then we are very happy. If not, we have the other ways of aggregating it and still coming up with models, which are a little bit more complicated, will take more memory and more time to solve and stuff like that. And then let us say we have multi-zone building model. How are you gonna actually, there are 2 ways you can train the model now, or estimate the model. You can individually look at, like, you can just look at perimeter zone 1 as an independent zone or an uncoupled zone, and just create a RC, or learn a RC network model for it. And basically learn an RC network model for each of the zones independent of each other. And that would be an uncoupled architecture, and which should basically give you bad results. Okay, but then it wouldn't be as complicated to learn. And the coupled architectures would be where if you have n number of zones, all of the n zones are coupled, and you create a model which is like one single model for n zones, and which is coupled, and which should give you a better result. Sorry for that. Okay. Okay, so, all right, so that is how we process data, and that is how we can develop our models. Going further, this is some modeling. We can return back to it if we have any questions, but for now, I think this should do. So the idea is, like, once we have learned, so if you can see this over here, this over here is the thermal model. Like, this can be either learned through ANN model, or we can learn the RC network directly through gray box techniques. But this entire thing is showing you a simulator of a single building, which will be present in the Helix co-simulation platform. And the way it would operate is, you would have inputs going into the building, which are ambient temperature, solar irradiance, that is weather. Then you have all the disturbance coming from people and equipment, and then definitely the HVAC control that you can have. And this input is exactly like Energy Plus. Okay, so and this input is then getting converted into all the different kinds of heat gains that a zone or the building might experience. Like QSOL 1 and 2 are the heat gains due to solar irradiance. QIC and QIR are due to internal heat generated from people and equipment. And then QHVAC is the heat rejected, accepted by the HVAC system. And in order to get the other, the 4 QSOL 1, QSOL 2, QIC, and QIR, you have to create some regression models so that you can go from the Energy Plus inputs to this QSOL. So we have to learn that, and Energy Plus helps us learn that. Like, we learn those regression models to generate QSOL 1, QSOL 2 from GHI, for example, using Energy Plus data. Once you have all those regression models and your ANN or RC network model, you can basically have a discrete time building simulator, which the output for which would be the next time steps temperature and your real and reactive power, what it consumed, which can go to the, like P and Q can go to the co-simulation, go to OpenDSS, and then TZ can basically go to a controller so that it can take the next action. All right, so yeah, I would need to go back to over here. So if you can see the thermal dynamics, they're the same two equations, that it's an ODE and it's a linear ODE, and hence you can write it in terms of x is equal to x plus BU. Over here, there is also a B2 for like disturbances, because WKs are uncontrolled disturbances, while UK is the controlled one. So we want to make that distinction. And X is your state, which is nothing but your zone temperature and the fictitious wall temperature. And then 3 and 4 are the actual physics model that you want to learn, but we're now talking about how to learn them through an ANN. So those would be approximated by a function f in 17, where it would take in x1 of k, u of k, w of k, that is the state, the current state, the current controllable input, and the current disturbance, and it will produce for you the next step state, that is the temperature of the building. So keeping that in mind, there are different ANN architectures that we are currently trying to test out. And so this is no standard nomenclature that I have used. So I call this one time stepper 1, and it is not a neural state space model. So basically, it is a vanilla neural network where it will take like the X, U, and W become the complete input vector, and you learn some theta because you know X1 from your training data. So that's time stepper 1. It's like your network gives you the next time step state directly. Other one is the same thing, but your network now tries to actually learn the derivative of it. And you have to add the previous state to the thing. And this has a kind of smoothing effect on the training and also the results. So this is time stepper 2, but still not a neural state space model. So time stepper 1 and neural state space model would mean I will train two different.
Sorry, it seems that somebody has a question. Do you want to take question now or at the end? Which one do you prefer?
Sure, I can take a question.
Maybe see that.
I don't think I can.
Hi. Can you hear me?
Yes.
All right, great. Thank you for this presentation. This is Bora Akil from PNNL. I missed a step here. You described how we can model buildings relatively well, and we have been doing that for a long time using mathematical models.
Right.
And then you jumped to the neural networks. But
Yes.
I missed the motivation for why we would want to use a neural network to model the building space. So can you please say maybe a sentence or two about that motivation? Thank you.
Right. Okay, that's a great question. So yeah, sorry for that I didn't provide enough motivation why we should use ANN architectures, or why shouldn't we just go to gray box modeling. So the thing is, I'm trying to replicate Energy Plus's model into a particular model so that I can use it at scale, like multiple number of these buildings into a co-simulation platform, which I wouldn't be able to do with Energy Plus with the computing hardware that I have. And because the other thing is, the idea for this is because the machine learning training paradigm, you can use a lot of data to train it. Not like, let us say, you set up a constrained optimization problem to learn the RC parameters. Maybe you can do it with 3 days worth of data, 6 days worth of data, and then it is good locally over there, right? So in order to look at the rich input space from the data that I'm generating from Energy Plus, I would want to have these models because they are going to be part of a simulator, and I want them to be basically they should have seen all the input space, and And in my opinion, or rather, or with my technical ability, I think at this point that gray box modeling techniques will basically look at a small section of that data because the way they formulate that problem. And it might have changed with the neuromancer thing, but I am not going there now with parameterized.
No, I understand now the motivation, and it makes sense to me. Thank you very much for answering the question.
You're welcome. All right, moving on. And then, yeah, and time stepper 2 is nothing but you learn the derivative with 2 different neural network models. And over here, the A and B, the subscripts A and B mean, or they're supposed to mean the A and B matrices analogy for these neural networks. And also this entire exercise is because there is no central place where we can see that all of these have been applied to building data and seen what results we get. So that is also one motivation to look at all these different models, because I don't know which one is going to work better. But in literature for dynamical models, these are the basic kind of ways you can train a neural network to do that. Okay, any questions? Okay, let's move on. Oh yeah, and then you can use MLP, RNN, LSTM, GRU. That is what I'm using to populate those models in a particular way. And if you look at some results, so these results are for time stepper 1, not a neural state space model. And as you go, like each row is the different kind of neuron that has been used to create the layers. And the columns represent the aggregation zones, and this is still the 5-zone. The actual building is 5-zone, the small office 5-zone building. And to take the gist of it, the blue color is for the coupled simulations. The red color is for the uncoupled simulations, and the black is the actual temperature. So just having a look at it, it can be seen that the coupled version learns it better. And the weirdness that you might be seeing in the other ones is because we haven't done hyperparameter tuning properly. And we have also restricted ourselves to the data, like we haven't messed with the input or the schedules so that we can get more richer data out of the generator. So there is some scope for improvement, and we are working on it. All right. Okay, gray box model. So this is like something we are trying to do, and very open to take suggestions. So basically, discrete stochastic ODEs, and yeah, apologize if that is not an exact stochastic equation, but the QK and the RK are Gaussian noise processes, not processes, but rather they are distributed with a zero mean Gaussian. And if you can represent your ODE in this fashion, which we can do for our linear ODE system for the thermal dynamics, then you can learn these parameters with a Bayesian setup, and that is gray box model estimation, where the data is that you can only know the output. And the output is the measured quantity, which is just going to be the zone air and not the any other temperature state that you might model. And basically, Bayesian setup means that you compute the full posterior and then work through it. And the way to work through it is basically through Bayesian filtering and smoothing. If people have heard about Kalman filters, that is a specific closed form solution for a linear system with additive Gaussian noise. And these are basically the Chapman-Kolmogorov equations for filtering, and then you basically get the filtering equations from there, but these are very general. These can basically be converted into any form of filters or smoothers that you know of. and they come from here. And these help us in doing at least the state estimation. And I'll be sending out this PPT, and there is a link to a GitHub repository if you want to use the Kalman. Like we have developed almost all, apart from particle filters, we have developed all the filters and smoothers, and I think it's a good package to use if you need to use that. So the other setup is like what the actual problem is. Like we are in this model estimation paradigm, and we saw that through filtering and smoothing, we can at least estimate the state. But we want to estimate not only the state, but also the parameter. And then the setup becomes a little different, where you need to have a prior on your theta and the theta, and then you have everything conditioned on theta as well. And over here, the data is, you still don't know the hidden states, you don't know the parameters, but the only thing that you know is the measurement that is coming out. Difficult, like to think about it, it's a difficult problem. And then even over here, you have the full posterior, and then you get around with it through marginal posterior, and then you work through it, and you see that the filters and smoothers help us later in actually computing this thing and actually coming up with the joint state and parameter estimation. So the algorithms currently, our work is in progress that we are currently utilizing are I would call it a naive NLP, and yeah, I would just go fast. If anybody has any questions regarding anything, just raise your hand or shout out. But yeah, this is a naive NLP. It is a constraint optimization problem. So to minimize the squared error between what you have observed and what you would be estimating as y. And then the constraints are nothing but your dynamics and the output equation. And then you have constraints over your states if you know what constraints there should be. And if you know some good constraints for your bound constraints for your theta, they are welcome too, because you can do that. The other one that we are trying to see is the state augmentation method, where you basically augment your dynamics with your parameters and then utilize the filter to simultaneously estimate state and parameter. It is not a foolproof solution, but it is like one thing that you should start off with. If it works for you, it is good. But we will have a more concrete discussion on it once we have all the results ready. But this is like one of the easiest way to set it up if you have that package, or rather if you have your own package for doing Kalman filters or the other types of filters, because over here the filters wouldn't be Kalman. They would have to deal with nonlinear systems as the state would be augmented. Then you have a very famous the batch estimation, which is basically a math maximum ape posteriori estimate. And this is a particular way of framing it. Is a very general way of setting it up. And the other one is an MLE, maximum likelihood estimation, and it basically infuses your Kalman filter within the constraints, along with basically it's a Kalman filter in there, and you're trying to minimize the one-step prediction errors that can happen when you run that filter. And these are, so the other things that we want to work and compare and see which ones to go for are energy function-based methods and EM algorithms. For brevity, we wouldn't go, like I haven't created slides for the mathematics of it, but we will have results for those as well. So these are all the algorithms we're trying out on the building data that we have generated from EnergyPlus. And then I would like to work on, move forward by basically going into physics-informed neural networks for moving into the future. And then we have a really good candidate, neural ODE. And I would like to also see if there is any extension possible with physics-informed neural ODE. Like I'm trying to develop a formulation for the pin, and with the kind of, because it is an inverse problem for me as well, because I do not know, I have no access to the RNC parameters. And I do not have access to the state as well. So it's a little tricky of how you could get that to work, at least for me at this point. So these are hybrid models where you are combining both machine learning and physics. And yeah, I plan to work on them and get a good hold on them and come up with some results. Any questions?
The last slide or?
Yeah, 5 minutes, five to 10 minutes. Is that okay?
No, that's good. No, because you asked the question, I thought that.
All right, so we have looked through the mathematical modeling. We saw that we can come up with simulators and test benches and stuff. We saw like the elephant in the room is the thermal model for this large scale simulation. And we saw a few techniques that we can use from gray box to black box, and how to identify that model and convert it into a simulator so that we can use it in our application. So now we should look at what is the control, like how can you actually do the control if you have all of these things. Okay, so we assume, so this is like, this slide is something that we are targeting for at some point. That this is what the entire thing would look like. That we would have buildings, which are those models that we saw, and they would have their own local controller, intelligent local controllers, basically operating the building. And these buildings are basically connected through distribution lines through OpenDSS and the Helix simulator, and that's our plant. That is the thing we want to control. The disturbances, as always, are ambient weather and occupant behavior. And the objectives are like, what do we want this system to do for us? We want it to produce some ancillary services like help us in flattening the duck curve. We want the buildings to reduce energy usage, and we want, and still like even, and the most important thing, do all of these things while maintaining occupant comfort. Otherwise, yeah, it wouldn't be like a good control strategy. So how would we do that? So we are envisioning, not envisioning, this is like out there in literature. It is about how we model the aggregator. We're not there yet, but we think an aggregator would need to have some kind of weather forecast. It would need to do some load forecast. It would need to have some understanding of the network model. It would need to know about the occupant model, definitely the thermal model. And then based on all these models and forecasts, it can come up with a controller which can send an action. And for us, the action would be a price signal sent to the buildings. And the local controllers would take that into cognizance and change their behavior. And the price signal would be such that the aggregator is the real intelligent guy here. Like he knows his the buildings that he's controlling, and he knows exactly at what price point can I get this group of buildings to do what I want, and that will be a kind of a game between them to do that. And that is what we envision happening. And for that, we are trying to get everything built. And yeah, that was the purpose. That is the purpose of this talk, to show that what we are trying to do and where we are at. So this is where we, this is what we intend to do, slowly and steadily. The other thing is like, what kind of control are the local controls? I'm not going to touch aggregator at this point, but you would be like local controller, like what is a local controller? What is an intelligent local controller? An intelligent local controller has to be based on some kind of an optimal control paradigm. So the easiest ones to understand are, or rather applied to buildings currently, are MPC, that is model predictive control, and RL, that is reinforcement learning. So we'll see a use case of each of those quickly. So model predictive control for a small house. So this is basically model predictive control converts a control problem into an optimization, which it solves at every step. It takes in information. It has some future information. It has the dynamic models for the like over here, the dynamic model is the refrigerator, because this is a small house. The objective basically is to maintain habitable conditions inside the house with just a small solar battery, small solar PV and a small battery system after a hurricane has hit and they don't have access to grid. And they might not have access to grid for foreseeable future, like Puerto Rico, 6 months, who knows? But they have the system. And we need to come up with a controller to help them basically survive. And survival over here would mean like my food doesn't go bad. So my refrigerator is always almost served. And then I should get light during the nighttime. And maybe I should get fan when I sleep. And that kind of a thing. So it is a small system. And then it can be formulated as a MILP or mixed integer linear program because of the on and offs that have to be done for the fridge and the secondary load, which is nothing but the lights and the fans. And it turns out to be MILP. And you have a cost function. I will not get into it. It tries to achieve the objective that I just said. You have some constraints. If you just go over it, the constraints are nothing but dynamic constraints, which is like you have the dynamic model of the battery, the thermal model for the refrigerator, you have some energy balance constraint, and then you have a bunch of power constraints on it so that you can tweak the solution to the way you want. Okay, so this is what we got. So the columns represent the controller, the rows represent primary load, that is nothing but the refrigerator, and the secondary, and the second row is the secondary load, that is the combined lights and fans that were served. And if you can see, the MPC controller did better than the baseline. And it was able to do better because it had some future information. It was based in an optimization problem, and it could basically make good trade-offs like we do when we have choices. Like we make good choices because we have intuition. We can see the future, and the future can be seen through either data or the dynamic models. And hence the models are very important because the models are needed here if you do a model-based control. I think me and Shishir worked on a paper recently. I haven't put the results here, but we have controlled HVAC in a house in certain kind of situation, but a more complex problem. We can discuss it later. But yeah, this is the MPC for this house. Now the similar problem. Now the problem is you have this house, you have this controller which is based on MILP. I have used Gurobi to solve it. Gurobi is a commercial solver, okay, and I used a good machine to solve it. And you wouldn't want to have I don't know, like a PC running to run your optimization in your house, right? It should run on something which is like maybe a Raspberry Pi. It is local and it doesn't take as much power. It doesn't need computing. But if you formulate your problem as an MILP, it will be difficult. You would have to write your solver on your own, which I'm not ready to do at this point. So I would look for some other options, which is, can I do the same thing with simple computation? Like when I'm doing real-time control, that control should be simple. It shouldn't be based on a solver like MILP, or it needs an MILP solver. Can I do it? And yes, the answer is yes, you can do this through reinforcement learning. And there are two paradigms, not two paradigms, but there are two parts to reinforcement learning. One is because it is a machine learning technique, you need to train it. And then the other part is that you implement it. Everything is done currently on a simulator. So it's, yeah, so it's the same problem. To train it, and we are training it with the ZapQ learning algorithm. It's from Sean Mine, University of Florida. It's the faster version of Q learning based in matrix gains and ODE flows and all that analysis. But a good algorithm of a step up, I would say, a ladder up from Watkins Q learning. And then you can implement it, basically. Basically, the thing that you need is you need to provide the agent a state or an information vector at time t. And you should be able to give it a cost, like what. So over here, I'm relating it to cost because I have that control engineer in me where there is no reward, but it's all cost. So I do not talk in terms of rewards here. So you basically, so cost is nothing but reward. Either Yeah, so you basically provide state and cost. Based on that, the agent learns, and as the training progresses, it takes better and better actions based on the state it is. And once the training is done based on certain parameters, nothing but your hopefully all of your thetas that you're trying to learn have stabilized, and then you're like, okay, let's implement it. And implementation over here is very simple. It was just a minimum over 15 values because we have 15 discrete control commands. That's all. So if you learn the Q function over these U's, you just have to figure out, like, you compute the Q function at xk, you get 15 values, and then be like, which is the biggest, which is the largest? In this case, because it was done with cost, which is the smallest Q value? And that, the U relating to the smallest Q value based on that state is the best U for you. And you go forward with that. Yeah, we don't need to get into MDB basics, but you need to get optimal policy. You have a definition for Q function. You want to minimize expected discounted cost. And basically, argument of your Q function, optimal Q function, is your optimal policy. And yeah, and the ZapQ learning algorithm helps you learn that Q function in an optimal manner. The state space over here, this is interesting to look at. Like, what is the state space? It is the current battery SOC. It is the current fridge temperature. It is the current house temperature. All of these things, a little bit of future information, but there is this reinforcement learning guide doesn't have information about the model, as I said, this is a model-free thing, algorithm, and where the MPC had a battery dynamics model, with which it could actually compute within itself what will happen to the battery. Over here, it just knows one value, like, what is my battery currently? Okay, that is the information you provide. You have all these possible actions, and there are 15 feasible actions. If you go through it, it's quite simple. Our state space is infinite, and our action space is finite. This can be handled by Q learning, and we are very glad that that happened. And then you do some, you create a reward function over here, a cost function. You want a cost to maintain your refrigerator temperature. You want a cost to keep your battery alive. So all those objectives that we talked about in the MPC can be actually formulated as some kind of costs in an intelligent manner over here. And we don't go through the math of it. If somebody has questions, we can go through it. But yeah, we have all those. Yeah, and then we use a linear approximation for the Q function. We have a particular basis function. We have a particular f of x, and we need to learn 435 parameters. And real-time control is just argument over 15 values, and very quick real-time control once it is trained. Training is hard, and there are a lot of things that you need to take care of, similar to hyperparameter tuning in machine learning. And then these are the results. The black plots are for the baseline. The red plots are for the MPC, and the blue plots are for the RL. And the RL didn't perform well. It performed really well for maintaining the fridge temperature. It didn't optimally do it as well in terms of battery management. Like, you can see the red one, like, it touches to 0 and then it starts charging. Like, it knows that the model information comes into handy there. And then yeah, it wasn't able to learn, like, how to provide for the secondary. And that is something that you have to tune and get it done, like, and which, yeah, sometime in the future definitely would try to do that, but not in this problem, some other problem. And okay, so that was most of the talk. I'd like to conclude. Okay, intelligent control depends upon, like, you need linear algebra, probability, optimization. You need some estimation knowledge. You need optimal control. You need machine learning. So yeah, there are a lot of, like, It has been, I have been in grad school long enough that I was fortunate enough to go through all these courses and understand something. But I know it's a challenge. If anybody is interested, I am going to start like a summer group study for this, like covering all these aspects. If somebody wants to do or do a group study, make their summer more productive. I want to study more, and it helps me to study with others. It makes me more productive while studying. So that is something that I would like to do. And thanks to my advisor, Dr. Anamika. These are all my collaborators. I think everybody is here apart from Cassie, and she has done a phenomenal job with the data generation. Is Kunal here? Oh, he's here. Okay, yeah, thank you guys. If you have any questions, yeah.
Okay, yeah, thank you. Very interesting talk, engaging, everything perfect. Let's go to the fun part, the questions. Anybody has, oh, let's go first online. So anybody online, if you have questions, please unmute yourself and ask your question. Okay, so then go back to people in the room.
Yeah, I have a question about your model parameter estimation. So I think I might have missed it. So what are the inputs while you are trying to estimate the parameter of your models, and how do you do it?
Mm-hmm. And which one? Like the gray box?
The gray box, yeah.
I've kept it simple because it
was a nice presentation.
Thank you. And simple in the sense, even in terms of like modeling it for either cases, it's the same. It basically stems from the two-state ODE model. And hence things become a little easy to manage. Get there. Oh yeah, here, right? So if you want to learn an RC network through gray box, or you want to learn an ANN, basically you want this, right? You want the model to give you this if you give it EZK at K and all the disturbances and the control, you want it to give you the next state, right? So these are, so you need ambient temperature, you need all these heat gains, and you need your heat gain from your HVAC. And those are the consistent inputs that I'm using to generate estimate either an ANN model or an RC network.
So right now you are getting this from Energy Plus?
Yeah, so I'm getting all that data. The input data comes from Energy Plus in a particular manner. Okay, the regression that happens over here. So basically, Energy Plus definitely gives me QSOL1, so that I can basically create a model between GHI and QSOL1, so that because Energy Plus will be doing it in a more white boxy way with more equations and more detail. And I think that detail can be captured enough, not exactly or accurately, very poorly maybe, but that is seeming to work over here. Like we wanted to keep it simple, and definitely the QSOL1 and QSOL2 are not linear, but we still have the linear models. We would like to make like they are non-linear with respect to GHI. It's because of the building geometry and the placement.
So if I want to model a real building, so what are the measurements that I need to have in order to have the model?
So at least you should know the energy consumption. That gives you this kind of a data, like a proxy for people, lighting, and equipment. And then you need to have some kind of a HVAC related information, like what is HVAC exactly consuming, and definitely the temperature of the zones. Like at least that data you should have to start off with a basic model to do it. Yeah.
Thank you.
You're welcome. And the idea is, like, think about it. This ANN model, let's say a building has a IDF, like a Energy Plus model. We know a way to learn this ANN, okay? And that ANN is learned for just that, just the inputs coming from the Energy Plus. So maybe there can be, this model becomes static after learning, and you put another model, and then you learn whatever you actually get from the building, you transfer that and convert that over here. Like you learn other, means that can be done. I don't know how effectively, but these kinds of things are being used, and that is some like future work that we would like to do in that direction. Yeah. Anything else?
So yeah, I'll go for the other question.
Sure.
So this about the Docker that you started with. So you said that it has like it requires really a high ramp rate to fulfill the demand, right? So is there any quantitative number or something which would specify what is the impact of HVAC on the steep rising of Docker?
Okay, think about this. I don't have exact numbers, but I can give you some answer logically. Let's think about commercial buildings. Okay, let's say that there is a compressor somewhere, which is basically providing this HVAC. This compressor can be slowed, can run at different speeds or whatever, that, and then it can consume different powers. If you're able to harness that, like let's say you are able to lower the HVAC consumption by let's say 5% in each building across Spokane, let's say. So you have some flex, right? And that can be done quickly because you just have to ask the compressor to, or the fans in the ventilation to change. And how fast is, what is the dynamics of a fan slowing down or speeding up? It's quite quick. So it's like at command that you can do it.
My thinking was the dynamics, the thermal dynamics should be really slow and it should not have like really fast requirements to do it. So it should not be affecting much of that ramping during the evening or the neck of the Docker. That's just my simple understanding.
Think about this, like if you are at home and if you turn off your AC, it will be at least half an hour until you feel something. So maybe we will stop doing that for you, in half an hour we'll do it to him. And you alternate it with groups of people, and that is intelligence coming from aggregation, which Atul is working on currently, and we will have something to talk about more once we are into it more. Yeah.
It's something related to what he is asking. So have you seen any studies or document that talk about how much flexibility you have and how much impact you can have on the overall system? So, because you know that all of these, they have costs associated. So you have to install some sort of automation at each building and so on and so forth. I see that it may have direct impact at the peak load. So because then over there you have to actually install new generators. I mean, this kind of a study. So you may comment on that one. If look at the bigger picture. So how these things will affect the whole power grid.
So I think it in terms of there is flex, definitely. I do not know exact numbers, but I worked with Edo, and all of their work, like a big chunk of their work was to determine how much flex do they have from the people that they're going to, or they already have a relationship with. Like they can get the data, maybe send in some control commands. So there is flex. And the point is, if we are successful in harnessing that flex, we will offset the capital requirement for other things. And this is not a complete solution any which ways, but even other things like we don't want many gas power plants. So maybe if this can offset 2 gas power plants from Spokane, well, that's the flex we have. And the other thing that I didn't touch upon in motivation because I was tired to make a slide.
That's good. You're good.
Is that like with these things like being able to do bidirectional power transfer, there can be network congestion which we haven't thought before about. And being able to help with that, the aggregator should also have network knowledge. And if not with that thing, at least network congestion can be managed. So that is also one thing that can happen with this.
Nice. Just quick question. So about those, when you define those zones, how do you define it? What is the meaning of those? I'm sure you know that. But
Yeah, so this room, if it has a thermostat, which means if I change the thermostat, there are these vents which will be affected through the building control system and be like, okay, stop the airflow or increase the airflow. So that particular volume, this volume in the building whose temperature can be controlled independently, is called a thermal zone.
Oh, so then in that building, there are five regions that they can be independent.
Independently, temperature can be controlled, yes.
Okay.
But because they are in contact with each other through walls, there is some coupling in the heat transfer. Okay,
nice.
Any other?
Yes. How much control would a customer maintain over the over their HVAC, and how would you get them to trust or maybe incentivize them to have the control be done elsewhere?
Right. So the way we are thinking about it is a house or a building will have its own intelligent controller. It will have its own objectives. One of the objectives will be, should I support the grid when the grid sends me some signal, the aggregator sends me some signal? How you want to apply that? Maybe you are like, no, I don't want to support it. Somebody is like, yes, I will support it. Maybe tweak that parameter over there. So it is completely under your control. The only thing that then comes into picture is, do you want to be in this program? That is also like, do you want that term in your local controller, first of all? So, and I think currently what they are doing is, because this is like proof of concept work now, so they are basically trying to pay people to become partners and see what happens. But in the technology, we are a little bit away from like mass scale adoption. There are like pockets in which, like, I think definitely PNL is working a lot, and there is Lawrence Berkeley Lab, which has like is complete nuts over this kind of work, and they have a complete building and done in like real-time control with a lot of sensors, a lot of estimation, everything, different kind of a tool chain and stuff. But yeah, it is going to be, it is like a new technology coming in and be basically making the consumer, educating the consumer. Basically, it is finally their consent. You cannot force it up until it is, I don't know, it won't happen here, definitely, but yes.
Great presentation.
Thank you.
I may have asked you these before, but just a couple of quick questions. So here you follow the simple basic 5-room model. So how does your model, because you're aggregating these 5 zones into one zone, how does your model scale if you look at a larger model where you have many, many zones? Because then the data you get from Energy Plus makes your MIMO model very, very large, very, very fast.
I hope it should work good, but the answer would come after the summer when we start using Kamiak, and you are going to help me. Yeah, cool. but yeah, we want to try it out on like all the possible buildings, and at least like this is so many variations, right? Some buildings have like 40 zones. Okay, like how many variations of this you would want to do? So my plan is get everybody to one zone. Let's see what is the one zone performance, and then talk about report. Right? Like at least we have a fixed, some concrete way of doing it, and then we know if there is enough time and enough people and enough automation, you can keep on creating it and checking it out. But yeah, definitely a plan to do all the 16 different types of buildings as a single zone, and doing all these models and basically coming out with which model is the best. And I really hope the physics-informed ones and the physics-informed neural ODE one should, it is difficult to formulate, I'm still learning, but if that turns out well, it has all the characteristics which this problem requires. Like you need some physics, there should be physics, but I haven't seen anything which does like neural ODE along with pins or rather equations. And then the other thing is that everything that I see, there is no control. Everything is a state. Like every ODE is just talked about as a state. It's difficult to get some paper or something where we talk about explicitly, this is state, this is the control, and this is how PINS is going to work for you. Okay, or neural ODE is going to work for you. So it is always like the traditional ODE thing where there is no control, but rather just the state working through, like, at least what I have seen. And I'm trying to find out more.
Sure,
but,
sure.
Yeah.
Okay, thank you.
Yeah, welcome.
Okay, last lucky person. You're a lucky person.
I'm trying to relate this with the dot curve because it actually looks like this is a solution that can be implemented over like the 24 hours of a day. It doesn't have to be just at the ramp, right?
Yeah. Yeah.
So I'm trying to understand why why it has a peculiar importance for the ramp when it can actually be used like
Yes.
24 hours of a day.
But I had to motivate it.
Okay.
And duck curve gets us going.
Okay.
So I know it can be used throughout. And the other one, I just couldn't make the slide, was about like network congestion because they are not just consumers, but prosumers. And we don't know how bidirectional power is going to play out. And the other one, I think, is, yeah, they are a good resource. Like this is the flex. This is a virtual battery. Like because you can turn it off, turn it on, even at half-an-hour intervals, you're not going to feel anything. Like the thermal inertia is there, and that has to be exploited in one way or the other. That's an intelligent way to do. It's an intelligent approach to do it, rather than so these become virtual batteries, and then maybe we do not have enough flex, and we then put in some more batteries, and then we have a good integration of PVs, I guess, and wind.
So in modeling your battery, did you include, like talking about the dispatchability of the battery, like did you use maybe like cycle charging or load following kind of dispatch or
So the battery is very, so control, you mean, like what kind of control does it follow?
yeah.
Whatever you like.
Okay.
Yeah. Like it is just a model. So the way you want to control it, I'll give you the control commands. Like these are the things you can change to make it work. You figure out a way to do it.
Okay, one more round of applause. So, thank you for great presentation.
Thank you for having me.
Yeah, appreciate that. Okay, good. Thank you. Yep. Okay. See you guys next time.
Great presentation, Nina.
Thank you.
Yeah, that was great presentation. And thank you for doing such a great job in that short time. So I really appreciate it.
Thank you. Thank you for giving the opportunity.
Actually, the time
Jameen, is it okay to shut down my PC yet?
our guys kind of used 15 minutes to serve the food before everyone got ready.
You didn't ask me a question.
So what about people's cell phones? Like, you don't take them into account?